In this section, we are going to continue our study of probability. So, just to back up for a second, the motivation for this is that we are going to spend a large portion of this semester discussing something called statistical inference. Effectively, after we finish probability, that's like all we're going to talk about. And in this, we use a sample characteristic to infer a characteristic about a population. And if we take two different simple random samples, like suppose, for example, we're trying to infer the average weight of male students at UAF, we would take a sample of people and find their average weight and want to ask ourselves, how similar is this to what the average weight of all men at UAF is? And if you take two different simple random samples, the characteristic is going to be different comparing those two groups because of variability. And then my average weight in group 1 would be different than my average weight in group 2. And we want to just know how much variability can there be. And one problem here is that you could see an effect in the sample that isn't really present in the population, or see no effect in the sample when one really is present. So in that case, you could think of something like a drug trial, like maybe this drug appears to be effective from the study that you did, but really isn't. Or maybe the drug really is effective, but you don't see it. And we are going to need to acknowledge and measure the probability that these things happen. And this question is just an example of an interesting question that you will be able to answer using some of the stuff from this lesson, or this unit, not this lesson specifically. So there has been some controversy over the use of mammograms to screen for breast cancer. And some argue that the dangers of false positive results, and a false positive means that you test positive but don't actually have the disease, and these result in unnecessary treatment, outweigh the benefits of early cancer detection. And we assume that 0.8% of women who get mammograms have breast cancer, and in 90% of the women who have breast cancer, the mammogram will correctly detect it. However, among women with no breast cancer at all, about 7% will still get a positive reading on the mammogram. So after we finish this chapter, you should be able to answer this question. If you get a positive reading, what are the chances you have breast cancer? And here's a surprise. It's not 90%. It's actually more like 10%-ish. So, and that's because this false positive rate is relatively high. So if you have a positive test, you kind of have two options. Either you're actually sick, which happens, or you are a false positive. And the false positives are so much more numerous than the real positives that if you have a positive test, it's quite likely you actually don't have cancer, and you really should ask for a second test before you agree to treatment. Okay. Now, recall that there are two conditions for valid probabilities. They have to be between 0 and 1. This inclusive means that 0 and 1 are also legitimate answers for probabilities. The sum of the probabilities over all possible simple events is 1. In other words, the total probability for all outcomes of a random circumstance is equal to 1. Okay, so on that note, suppose we have A, B, and C, and they are all disjoint possible outcomes for the same random circumstance. Now, this disjoint just means that they have nothing in common. So we have our sample space, and A B, and C live inside of it, and they overlap not at all. So tell me whether each of the following sets of probabilities is actually possible. So first of all, are the probabilities less than 1? And the answer is yes. So that part is good. So all probabilities are less than 1. And they're also positive, because you can't be a negative probability. And then you have to see if when you add up all of these probabilities, do they total to something that is less than or equal to 1? And then also, P of A plus P of B plus P of C, well, that's equal to a third plus a third plus a third, which is 1. So, yes, these are valid probabilities. And one more thing, because the probability of A, B, and C sum to 1, what that tells you is that in your sample space, if this is A, there you've got B, there you've got C. So somehow A, B, and C have to cover the entire sample space. That was not a requirement, but in this case, that's what's happening. Now, how about this case? We have P of A is a half, P of B is a half, P of C is 1/4. So far, no super big problem because the probabilities are each less than 1, but notice P of A plus P of B plus P of C, that's a half plus a quarter, or 1 1/4, or 1.25, which is bigger than 1. And that's a problem, right? If this thing is bigger than 1, and they were disjoint events, the sum of their probabilities should not have gone greater than 1. So, no. Okay, this last one. P of A is a quarter, P of B is a quarter, and P of C is 1/4. And the answer is yes. P of A plus P of B plus P of C is 3/4, which is less than 1, so that's okay. And nothing said that A, B, and C had to be all possible events, so if you had a picture of what was going on here, maybe what you have is something like this. There's A, there's B, there's C, and there's some leftover stuff that you just don't know about. So it's totally possible. These are valid probabilities. So suppose we flip a coin 3 times. List the sample space of all possible outcomes, and then find the probability of flipping exactly 1 tail, and the probability that you'll flip at least 2 tails. Okay, so our sample space, which I'm going to call S. Okay, so it helps to be systematic, so let's start by listing the heads. We could have had heads, heads, and heads. But there's only one way for that to happen. Now, we could have had 2 heads, which could have happened by having 2 heads and then a tail, a heads, a tail, and then a heads, or a tails, a heads, and a heads. And that's the way that we could have 2 heads. We also could have 1 head or 2 tails. So head, tails, tails is one possibility. Tails, heads, tails is one possibility, as is tails, tails, heads. And we could have had no heads, which is tails, tails, tails. Okay, notice there are 1, 2, 3, 4, 5, 6, 7, 8 possibilities there. And actually that counting rule we learned in the last lesson, you have 2 choices for the first toss, 2 for the second toss, 2 for the last. for a total of 8 possible events, which is what we got. Okay. The probability of B. So the probability of flipping exactly one tail. So look at your list and tell me how many of those things have exactly one tail. Well, this one does, and that one does. So the probability of B is 3 of my simple events out of 8 total events. Now C is the event that you flip at least 2 tails. What that means is T is bigger than or equal to 2. Or the number of tails is bigger than or equal to 2. So let's see. Well, there are these 3 that have exactly 2 tails. And there's another one that has 3 tails. So at least 2 means 2 or more. So there are 4 out of our 8 events, which is 1/2. Let's just add one more thing. And suppose I had said that the event D was that you flipped at most 2 heads, just vocabulary. So the at most means the most heads you flipped is 2, which means you could have flipped 0 heads, 1 heads, or 2 heads. So the probability of that event D. Okay, well, where you flipped exactly 2 heads, that's this guy, this guy, and this guy. These next 3 have only 1 head, which is less than 2, and this one has none. So that probability is 7/8. But at most means the number you're given is the most. At least means the number you're given is the least. Okay, so recall that complementary events, the complementary event of the event A is written A with a little superscript of C, and it contains all of the events that are not in A. And your diagram you should have in your mind, you have some event A complement is all the stuff outside of it. So suppose you're drawing cards from a standard 52 card deck. Let A be the event that you pick a heart. Find P of A and P of A complement. Okay, so for event A, you ask yourself, how many hearts do you have? I mean, not you personally, I mean in the deck. So in the deck, there are 13 hearts out of 52 total cards, which reduces to a quarter. And remember, for a complement, that probability plus probability of A has to add up to 1. So P of A complement plus 1/4 equals 1. And therefore P of A complement is 1 minus 1/4, or 3/4. You could have also found that by saying, well, if there are 13 cards that are hearts, there are 39 out of 52 cards that are not, which then reduces to 3/4. Either way. But the kicker to note is that P of A and P of A complement together sum to 1. Okay, now some more vocabulary review. Remember that 2 events are mutually exclusive if they have nothing in common. A mathematical way to say that is like this. A, that little upside down U means intersect. B is equal to this thing, which is called the empty set. And as a picture, remember that this is just, you have your event A, you have your event B, and there's no overlap. Now, we have some rules that we can use. If two events are mutually exclusive, then their probabilities of having one or the other happen is P of A plus P of B. If the events are not mutually exclusive, then this rule changes a teensy bit. So this rule only applies to mutually exclusive events. And if two events are mutually exclusive and the probability that they both happen, well, that has to be 0. And you can see that from this diagram. A and B have nothing in common, so the probability of something in A happening and something in B happening is 0. Just there's no overlap there whatsoever. So suppose we're drawing from a 52 card deck. Let A be the event that you draw a heart, B be the event that you draw a club, and C be the event that you draw a face card. Which pairs of events are mutually exclusive? Okay, so is drawing a heart, let's see, A and B. So is drawing a heart have no overlap with drawing a club? Yes. Okay, so A and B are mutually exclusive. Because there is no overlap. And let's just check. How about A and C? So draw a heart, draw a face card. So A and C has overlap. There are face cards who are hearts. So these guys are not mutually exclusive. That's my abbreviation for it. And then how about B and C? Does drawing a club have overlap with drawing a face card? This has overlap for the same reason. So not mutually exclusive. So only A and B. Okay. Find P of A or B and P of A and B. So P of A or B will be equal to P of A plus P of B. So the probability of drawing a heart is 13 out of 52. Drawing a club is 13 out of 52, which is 26 50-seconds or 1/2. Okay, A and B. Well, the probability of drawing a heart and a club, this really is saying like on the same draw. This is 0. Those two things can't happen. So the thing to notice here, actually is probably a good thing to say, is that I didn't say we draw twice. I just said we just draw a card. So really what we're implying here is you draw once. And you're trying to figure out how likely is it that on that one draw you get a heart, or on that one draw you get a club. And the probability of getting a heart and a club on that one draw simultaneously with only one card is 0, because your card can only be one of those things. Or something different. It could be a spade and it could be a diamond. So something that will help us deal with this whole independence issue is something called a conditional probability. So sometimes knowing one event occurs does change the probability that the other occurs. So suppose we have two events A and B, and remember that P of A is the probability that the event A occurs. Now, this thing, P, A, line, B, that is read probability of A, the line is read as given B. This is the probability that A occurs given or knowing that B occurs. So if you know B happens, what's the probability of A? And if you reverse that, P of B given A is the probability that B occurs given or knowing that A occurs. And the thing is that the thing that comes after the bar is some sort of knowledge you have. And that knowledge you have might affect the probability of A or B in these cases. So suppose that A is the event that you have some disease, and B is the event that you have some positive test result. What do these things mean? What does P of A given B mean? What does P of B given A mean? And I find it helpful to just actually write in words. So P A given B. So P of have disease given positive test. So this is the probability you have some disease knowing you had a positive test result. Okay. P of B given A probability of positive test given that you have the disease. So this is the probability you have a positive test if you have the disease. Okay, and then let's just look at P of A. That's the probability that you have disease. And probability of B is the probability that you have a positive test. Okay, and the thing to notice is that this A given B, that those things are certainly different. If you know you have a positive test, you're more likely to have the disease than if you're just a random person. And the probability of positive test, given that you have the disease, is going to be different than the probability that you just get a positive test. So yes, these are definitely different things. And we'll learn how to specifically deal with this guy, because that's a really important question to answer. What are the chances you have the disease if you get a positive test result? Okay, based on a survey of nearly all the 9th and 12th graders in Minnesota's public schools in '98, a total of 78,564 students reported proportions admitting that they had gambled at least once during a week during the previous year. And it was discovered that these proportions differed considerably for males and females, and it was found that all 22.9% of the 9th grade boys and 4.5% of 9th grade girls admitted to gambling weekly. So find the probability, this is written in your handout, but I have to write it in here, probability of being a gambler knowing you have a boy. And that is just this number as a proportion instead of a percent, so 0.229. Versus the probability that you have a gambler given or knowing that you are looking at a girl, that's just 0.045. So the information of the gender of 9th grader you're looking at influences the probability that this person is a gambler. All right, Now, here is a better way to know if events are independent. And from now on, I want you to use these three conditions here, not the sort of intuitive definition, because the intuitive definition kind of sucks. So recall that two events are independent if knowing A occurs tells you nothing about B occurring. But relying on this logic can be tricky in lots of situations. So to check for independence, check one of the following rules. So two events are independent if and only if any of the following conditions are met. So P of A given B is just P of A. And so look at what that means. Knowing B doesn't affect the probability of A. Similarly, this would be P of B. Knowing A doesn't affect the probability of B. Or P of A and B is equal to P of A times P of B. This probably is the most common way to check. So we're going to use that the most. So what you'll do is check and see if rule number 3 works. If so, this implies A and B are independent. If not, this implies A and B are dependent. Okay, when a fair die is tossed, each of the 6 sides, numbered 1 to 6, is equally likely to land face up. 2 fair dice, 1 red and 1 green, are tossed. Explain whether the following pairs of events are mutually exclusive, independent, both, or neither. Okay, so we have red die being a 3, red die being a 6. So are these events, first of all, are they mutually exclusive? And the answer is yes. A and B have nothing in common. Okay, are they independent? So let's use the rules. P of A and B. Now, because this is A is the red die being 3 and B is also about the red die being a 6, can your red die be a 3 and your red die be a 6 simultaneously? And the answer is no. So that is an impossible event. But when you check P of A times P of B, well, P of A has probability 1/6, 1/6, 1/36. So notice that those two things are not equal. So in that case, no, they're not independent, as P of A and B is not equal to P of A times P of B. Okay, red die being a 3 and green die is a 6. So are these events mutually exclusive? Okay, and this is tricky here because we have red die 3 and now it's the green die being a 6. So the answer isn't obviously yes or obviously no. So the question you have to ask yourself is, can you be both? So if you roll 2 die, could the red one come up a 3 and the green one come up a 6? So the answer is yes, you can be both, which means no, you're not mutually exclusive. Okay, are these events independent? And my intuition would say yes, because what happens on the red die shouldn't affect what happens on the green die. So I'm going to say yes tentatively, but I'm going to confirm that with this rule. So probability of A and B. Well, the pair red 3, green 6 is one combination of, it turns out, 6 choices for red, 6 choices for green, 1 out of 36 different possible combinations for those 2 die being rolled. And P of A times P of B, probably the red die is a 3 is a 6th, green die is a 6th is a 6th, which works out to be 1/36. So since those 2 things are equal, yes, they're independent. Okay, event A being red and green die sum to 2, and B is the event that the green die is a 6. So let's think about things here as pairs of red and green. If the red and green die sum to 2, that means both red and green have to be 1. So event A just contains the pair 1, 1. Event B, where the green die is a 2, so green is my second die, I could have had 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, or 6, 2. Those are the combinations. So looking at that, are these events mutually exclusive? Do they have anything in common? No. So nothing in common. So A and B share no events, which implies that yes, they are mutually exclusive. Okay, are they independent? Well, what's P of A and B? Okay, P of having A happen and B happen is 0 because there's no overlap. And P of A times P of B, well, rolling a 1 and a 1 only happens in 1 out of 36 pairs. Having the green die be a 2 happens in 6 out of 36. Anyhow, that's not equal to 0. So these events are not independent. Okay, so let's do a similar example with die again. Suppose you roll 2 dice, 1 black and 1 red, and you record the outcomes in order. Let A be the event that the red die is even, B the event the black die is odd, and C be the event that the die sum to 10. So list the events in the sample space S and the events in A, B, and C. Okay, state the number of simple events in each event. So just to save space, I'm going to write things. So we'll go black first and then red, and I'm just going to write them as 2-digit numbers, where the first number is the number on the black die, and the second one is the number on the red die. So for example, in the sample space S, and let's just think ahead, we have 6 choices for the first die, 6 for the second, for a total of 36 events. Okay, so in S, let's think about first if we had a 1. We could have had 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. That's 1 on the black die, and then all the other possibilities on the red die. Next, we could have had 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And notice that 2, 1 is different than 1, 2. 1, 2 is black being 1, red being 2. 2, 1 is black being 2, red being 1. Okay, and you can see next we're going to have 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, etc. And then the fours. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and then 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. And those are all 36 events. Okay, A is the event that the red die is even. So the red die is my second die. Okay, so I could have all the things where my second die was a 2. So 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, and 6, 2. All the things where my second die was a 4. So 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, and 6, 4. And then all the things where my red die, or my second die, was a 6. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. And you can see that there are 18 events in there, and you could figure that out as in the number of events in there by thinking for your second die, your red die, you have 3 choices because only the evens. The first die can be anything, so there are 6 choices for that. And 6 times 3 equals 18 events. Okay, B is the event that the black die is an odd. Okay, so the black die is our first die. Well, that would be 1, 2, 1, 1, 1, 2, 1, 3. So first die being a 1. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. And then 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. And once again, we have 3 choices for the first die because that first die has to be odd. Second die can be anything for a total of 18 events. Whew. And C, this is taking forever. C is the event that the die sum to 10. So think to yourself, could the first die be a 1? And the answer is no, because then the biggest the second die can be is 6, and 1 plus 6 makes 7, not 10. Okay, how about 2? Well, with 2, the biggest combination you have is 2, 6, and that doesn't sum to 10. And 3 is no good either. 3, 6 doesn't work. That's the 9. But on 4, 4, 6 is a legit combination that sums to 10. On the 5s, 5, 5 sums to 10. And then the other thing is that 4, 6 is different than 6, 4. Those are different events. So there are 3 events in C. Okay, now using all the information, having these lists will make answering the next questions quite a bit easier. Okay, find P of A and B. Are A and B independent? Okay, so A and B, let's just think about listing the things in there. A and B are the things where the black is odd, red is even. And we went in the order black first, red second. Okay, black odd, red even. So look at your list and look at the things that are both. Things like 1, 2 is one of them, where the first die is odd, second die is even. Things like 3, 2, 5, 2, 1, 4, 3, 4, 5, 4, 1, 6, 3, 6, and 5, 6. I'm just thinking to myself, I think there should be 3 choices for a black die, 3 for a red die, gave me a total of 9 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that checks out. So probability of A and B is 9 out of 36, or a quarter. Are A and B independent? Well, let's check that by finding P of A times P of B. So P of A is the probability that the red die is even. Well, we had 18 out of 36 things there in that event. B was the black die is odd. That was also 18 out of 36, which is a half times a half, which makes a quarter. So yes, A and B are independent. Okay, how about the probability of A and C? So in A and C, we had black, red, just to remind myself of the order. So C was the event where the die summed to 10, so that was 4, 6, 5, 5, and 6, 4. All right. So A be the event that the red die being the second die is even, so there are 2 things in there, 4, 6 and 6, 4. So probability of A and C is 2 out of 36, or 1/18. And then probability of A times probability of C. So A was 18 out of 36, or a half. C, 3 out of 36. So that's a half times a 12th, which is 1/24. And as P of A and C doesn't equal P of A times P of C, the answer is no. These events are not independent. Once we know C occurs, or once we know A occurs, the probability of A or C changes. If 2 events are mutually exclusive, use one of the rules above to determine whether these events are independent. Okay, so if A and B are mutually exclusive, then you know that when you look at what's in both of them, there's nothing there. So P of A and B has to be 0. But assuming A has stuff in it and B has stuff in it, this thing is going to be something that's bigger than 0. As in, this is just no matter what. And that's assuming that A and B have some events with non-zero probability. And notice that if P of A and B is 0, and P of A times P of B is bigger than 0, P of A and B is not equal to P of A times P of B, which means these events are not independent. So if you know that A and B are mutually exclusive, this implies they're not independent, or they're dependent events. So we are going to learn some more generalizable rules for finding probabilities where of one event or another occurring, or both events occurring. But for now, you can find the probabilities of unions, which are the ors, or intersections, which are the ands, by counting or listing the events in the union or intersection. So, for example, suppose you draw a card from a 52 card deck. Let A be the event that you draw a heart, and B be the event that you draw a club. Find the probability of A or B. So you know that A and B are mutually exclusive, which tells you that P of A or B is P of A plus P of B. But you could also think you have 13 cards that are hearts, you have 13 cards that are clubs. So the chances of drawing a heart or a club on a draw would be 13 plus 13 out of 52, which is a half. And the probability of drawing a heart and a club on a draw is 0. The card that you draw can't be both a heart and a club at the same time. So suppose you draw a card from a 52 card deck. Let A be the event that you draw a heart. Let B be the event that you draw a face card. And remember that there are 12 total face cards. We have a Jack, Queen, and King in each suit. So Jack, Queen, King, 3 things times 4. So P of A or B. Okay, so that's P of heart or face card. And the tricky thing here is that these events are not mutually exclusive, as in there are some face cards that are also hearts. So let's just consider how many heart cards we have. Well, we have 13 out of 52 cards that are hearts. And then let's add on the face cards that are not hearts. Okay, so if we have 12 face cards total, and 3 of them are hearts, so 9 are not hearts. So plus 9 out of 52, which works out to be 22 50-seconds or 11/26. And the tricky thing here was at this stage right here, you had to account for the face cards you'd already counted in the hearts pile. Okay, and then how about P of A and B? Okay, so probability of heart and a face card. So just ask yourself, how many hearts are also face cards? Well, there are 3 out of 52. And I don't think that actually reduces. All right. Suppose we have a sample of 7,000 naturalized U.S. citizens. We have the events given in this table below. So this table talks about ages. Find the probabilities of the following events. So P of A. What's the probability a randomly selected naturalized U.S. citizen is under 20? Well, in this case, there were 2,450 of them out of the 7,000 total, which works out to be approximately 0.35. Or you could say 35% of naturalized U.S. citizens are under the age of 20. Probably a lot of children in that. Probability of a complement. This is the probability that somebody is over 20. Well, that's the same thing as 1 minus P of A. 1 minus 0.35, which is 0.65. P of B. So the probability that somebody is between the ages of 30 to 64. Well, that's 1850 out of 7,000, which works out to be 0.158. And then finally, P of A or B. We'll notice that under 20 and 30 to 64 don't have any overlap. So we can find this using P of A plus P of B. Another way of saying that is that the events A and B are mutually exclusive. So that's 2,450 out of 7,000 plus 1,850 out of 7,000, which works out to be about 0.61.